where do you expect the most structural damage to be in a building, say multi-story building? Generally speaking, all sorts of caveats, towards the top of the building or towards the bottom of the building? Towards the bottom. Rami showed all these vectors representing the equivalent lateral forces from each floor of the building, and it's all accumulating. So the wall here is taking this weight laterally. This wall, or these walls, are taking those, and it's additive. So it's all things being equal, it's getting more and more demand, more and more stress out on it. So generally speaking, when you go and do a post-earthquake assessment of the building, the bottom is probably a good starting point when you look at where the damage to the structure is, and I'll get to you in 1 second. And then, what about the non-structural systems? Do you think the more non-structural damage will be towards the top or towards the bottom? Because it's moving more at the top. So the movement is what largely causes damage, both from the displacement as well as the amplified acceleration. Think of the ride that you're experiencing. If you're on the top here versus the bottom versus the ground, you're getting a much more amplified experience. And same thing with the non-structural systems. The suspended ceiling, your partition walls, et cetera, are moving more or getting more acceleration towards the top of the building. So there's likely going to be more non-structural damage the farther you go up. So you show up on a multi-story residential building, where are all the residents going to tell you to come look? It's always the people on the top floor units saying, you got to come up here, look at the cracks in my drywall on my top story unit. Where should you start your interior assessment? At the bottom.
Well, I understand that, but then most of the pictures you showed structural damage, 5th, 6th, 7th floor. Not just the facades, but like the actual, like the ones you were showing. Is that just poor design, or?
Well, we'll circle back on that one that had a bunch of damage up high. I guess I should reiterate the comment. The comment was a bunch of the photos we've seen have structural damage up high, and I just said it was down low. So what gives? One, I'll say, that's kind of disclaimer, all things being equal, and a bunch of examples that we've seen are, there's weird things going on in the buildings, irregularities, to use the terms we talked about, vertical setbacks and stiffness discontinuities where there's more wall and different amounts of wall. And you think of what we talked about with these dynamics of two different buildings. What if you have a building that's real wide and then sets back? You effectively have the same dynamic, pun intended, of different dynamics sort of compounding on the stiffer part of the building and the more flexible. So to some degree, some of the examples that we've seen that have vertical distribution of damage is that. The other comment I think that was made was a poor design. Well, just from a strictly efficiency standpoint, the ideal would be to design it so that the load and the capacity are equally proportioned such that that damage is occurring equally up the height of the building, which is not really practical in many cases. But, so all that to say, if there's a distributed damage, that's probably better than having all the damage concentrated in one spot, because you can sort of spread out the energy dissipation occurring within the material yielding, circling back to that force displacement graph that we talked about earlier. All right, concrete. Chapter 8 is inspection and posting of concrete structures on page 52. Again, a lot of the same isometric blow-ups of the buildings, et cetera. So concrete construction can occur in a number of different forms. There's structural wall buildings, namely shear wall buildings, frame buildings, i.e. moment frames. It can be cast-in-place concrete, where it's all poured and cast on site. It can be all these parts and pieces that are precast and brought on the site and attached together, and all sorts of creative combinations thereof. So it comes in a number of different forms. Rami showed this building earlier, or this slide earlier, which shows the various discontinuities or irregularities, vertical irregularities specifically in these various buildings. The nice thing about concrete is, generally speaking, the structure can be largely expressed in the architecture. So at least in these little graphics here, you can kind of see where the structure is as represented by the architecture. The exception to that would be concrete core wall buildings, a lot high-rise. You have one concrete core wall we talked about earlier around the elevators, and that's less accessible. But many examples we have today, you can see the coupled shear wall buildings and the concentration damage there, the vertical setbacks like we were just talking about, and the sort of dynamics of two different natural periods sort of interfacing right at that setback, elevation, soft stories, and hillside buildings. Another concept that I just want to take a second to deviate and talk about for this hillside building is, let's say all the columns on this building are equal, the same columns. So they're the equal cross-section, same reinforcement, same everything. We have shorter, stiffer ones, and then longer, flexible ones. You remember, say the columns are 2 times taller on the downhill side. From a lateral standpoint, do you remember how much stiffer the stiffer ones are? That's 2 times 2 times 2. So these stiff ones are 8 times stiffer. So if there is an earthquake for this hillside building, everything else being equal, where do you expect to see the most damage? The short or the tall ones? The short, which is maybe counterintuitive to some, because when we think about gravity, let me grab this guy, from a vertical standpoint, the short columns are way less vulnerable to gravity load. Here's that buckling of the spaghetti that Rami was talking about earlier, than the long columns. But from a lateral standpoint, of course this one's barely even attached, but the stiffness is dramatically less. The way we think about buildings as structural engineers is a series of springs in parallel and in sequence. And so it's very simplistic, actually even more simplistic spring model here. We have our stiff and our flexible spring. Your right is the stiff and your left is the flexible. So if I pull these, which one's going to take more than its fair share of load? The stiffness, or the stiffer, the right one. And then here's a depiction of that in sort of a plan view sense. So I lost my puller thing, but this is a much more stiffer spring than this. So a way to explain this, or example would be, if this is a concrete shear wall building, this more flexible spring would be a 10-foot long shear wall, and the stiffer one would be a 20-foot long shear wall. And so if an earthquake is shaking, this stiffer one is taking more than its fair share of load, particularly for a rigid diaphragm building, which is all to say a concrete floor and concrete roof type of building. And because of that, there's this sort of global torsional behavior. But the main takeaway as we think through these examples and as we look at damaged buildings is to recognize that stiffness inherently attracts more load. And so as we think through and looking for where the damage might be in a building, look for the stiffer areas first, because they're more likely to take more than their fair share. That makes sense? And so the key to concrete construction is, as Rami expressed earlier, is how it's reinforced. Concrete cracks and the reinforcement that crosses those cracks. So all that to say, reinforcement crossing those cracks is how reinforced concrete works. It's the concrete and compression, the steel and tension work together in this harmonious reinforced concrete world. And we discussed earlier, we like to see the damage concentrated in the beams or the spandrel or the coupling elements rather than the panels. So this 1964 Alaska earthquake example, to a structural engineer, this is beautiful. Wall piers are perfectly intact, and all the damage was designed so the weak link, the fuse of the system, if you will, are these coupling beams that did a lot of work. So there's different archetypes of buildings. The type C1 is a concrete moment frame building. This is just the FEMA graphic depicting that, where it's the rigidity of the beams and the columns, much like a table, where the rigidity of the connection between the leg of the table and the top table itself is what gives its lateral resistance. So you don't need a wall here for this table not fall down. You just need the leg of the table to be rigidly attached so that right angle wants to remain a right angle. So here's the isometric blow-up I think you have in your field manual. In Chapter 8, concrete frame construction. So here's moment frames. Here's the typical things you look for. A couple of terms to get used to. One is panel zone. So this is the interface where the beams and the columns meet each other. There's a lot of shear that occurs, so panel zone cracking there, beam cracking, and then column cracking. So which one is worse? Beam, column, or panel zone? I'd say column's worse, panel zone second, beam is third, if I were to rank them. Cracked infill wall, so the stiffness of this masonry infill wall in this example, and it's not designed from a structural engineer standpoint to be a shear wall, but has a lot of stiffness, much like those springs, and takes a lot of load first. And many times the crack that propagates from that stiff shear wall can protrude out through the reinforced concrete frame itself. Columns out of plumb at any level, damaged cladding or connections from the exterior cladding of the building to the structure itself. So all things to look for in reinforced concrete construction. So Rami talked earlier about, it got real loud all of a sudden in my head, about how we confine it, much like the mattress example, or the other example is a pop can. You have one empty pop can, the other's full of sand. That one full of sand, you can stand on it, hold a lot of load, the empty pop can crushes. And it's really a function of how large and frequent and how well detailed with the hooks that the bars are. So here's just a real quick example, sort of physical, tactile example of a 1970 uniform building code, non-ductile reinforced concrete column on your left, and this is a 2003 International Building Code column. So same, 8 longitudinal bars, same size, diameter, everything of the bars, but the spacing and detailing of these confinement bars makes a world of difference. I was going to pass it around, but it's kind of cumbersome, and you can come up and touch it with your own two hands if you like afterwards. So, really the effectiveness for reinforced concrete to be resilient, to be ductile, and to deform without breaking like a paper clip, and not like our piece of chalk is dependent on that detailing, despite as much grief our contractors may give us for making them do so. So here's some example of concrete columns. So here's some damage. I think that same example Rami showed earlier with the damage to the beam column joint, probably there. And then also some major shear cracking through the concrete column. So scale 1 to 10, vertical load carrying capacity. I think I heard a 1 and an 8 and a 7. We got a large spread here. Our standard deviation is significant. Lower. Yeah, inverse the 10 is good, 1 is bad, so a 2 instead of 8. Because those cracks are through those columns, it's intuitively very concerning. Another example of another 2 concrete concentrated in these deep beams, strong beam, weak column, not what we hope to see. This is the first story column that doesn't have that adequate confinement. So this is where those confinement ties, which are very limited and small in diameter, have essentially blown out as this mid-rise to high-rise apartment building has rocked back and forth. So in addition to its sort of 24/7 gravity load, there's a ton of extra vertical load that was expected of this column, and due to its limited amount of confinement reinforcement, the confinement ties blew out. Like you put too much load on the pop can, and the pop can blew out, and then now those vertical bars have nothing to restrain them, and they're buckling longitudinally. So it's concrete moment frame construction. Type C2 is concrete shear wall with bearing walls, and so our exterior walls in this example are both our shear walls are serving as part of our lateral force resisting system, but they're also a major part of our gravity system supporting for that 24/7 gravity load. So here's the other isometric blow-up. This is in your field manual as well. You can find the page. So I'll talk through. So this has a flexible wood frame, diaphragm, and the shear wall construction. So we're looking for shear failure. I'll point over here of the pier and the coupling beams, cracking, propagating from the openings, falling hazards, concrete parapet damage, diaphragm distress, and really the probably biggest thing is the connectivity between your diaphragm, your floors and your roof structures to the exterior walls from that heavy out of plane, that heavy wall trying to pull out of plane. Just explain that term if you're not familiar with it. So here's our wall. If it's being pushed on in this way, that's in plane. That way is out of plane. So just some of the terms that we tend to use doing this type of work. All right, so here's a reinforced concrete shear wall that's seen some earthquake, done some work, absorbed some energy. Scale 1 to 10, how much vertical load carrying capacity is left in this wall? I think I heard a 5 to a 9, if I heard it correctly. What do you say, Rami? Ooh, we give it 10. I don't know if, it's pretty close to 10. I'll give it 9.5, I think, just to give value to the scale. By definition, it can't be 10 because there's not as much as it was before, but I see your point. What about lateral? Sorry, I'm not to put you on the spot, just.
Car accidents are small, so I'm assuming the reinforcement is still engaged, so it's probably like a 7.
You give it 7? You don't want to give it more? Can I get it 7.5? You don't want to give it an 8? Hey, can I get a 9? Can I get a 9? You don't want to get a 9? I'll give it 8.5. Just intuitively, because of the nature of the cracks, rather than the one big X crack, the shear crack that we were looking at earlier, the reinforcement's done its job. It's distributed that cracking over the building. There's cumulatively a fair amount of cracks, but the size and the distribution of it, intuitively, we start to realize this is a 9.5 vertically and an 8.5 laterally, or whatever we want to give it. Here's some real world examples of that. This is some buildings that we assessed following the Anchorage earthquake a couple years ago in 2019. A parking garage with some shear walls at the end, some frames kind of penetrating out. I don't think that's a setback, but it's hard to see from the color. Just seeing what you see here, any estimation on what you would tag this building with?
Still being used, so it's great.
Still being used. At least people didn't get the car out of it after an earthquake. We don't know if they parked in there necessarily. So there's a pretty substantial earthquake, but it's less dramatic and catastrophic than some of the examples we've seen. So I heard a green. Any other suggestions? All right, green it is. It's done all work, it's been damaged. Presuming that the columns and everything we can't see are still relatively intact, we have no concern about the stability or gravity of the building.
Can you go back a slide?
Yeah.
Is that 3 separate pieces likely, or one piece? Because the cracks look like they continue through the lower. Is that stamped and colored?
Yeah, I probably should have addressed, I think what we think we're seeing is a solid reinforced concrete shear wall, so the structure and the confined concrete underneath the reinforcement is all consistent, but for architectural purposes, it's got the stamp and coloring and a little sort of lip and protrusion. I would consider that sort of exterior to the functional structural part of the shear wall itself. So it's not 3 walls, it's 1 wall with some pretty little lines on it.
Kind of a rabbit trail. Does that need to be repaired, and if so, how do you repair that?
Good question. There are ways to use different sort of, the risk if you don't repair it, I guess for everyone's benefit, the question is, does it have to be repaired, and if so, how do you repair that? The resonance is really bad right there. If you don't repair it, the risk is, water intrusion, acceleration of the rusting and corrosion and degradation of the building. of that wall over time. So there are different ways to use sort of epoxy and whatnot to repair the cracks, repaint, refinish, and make it look good as new, on the surface at least. Was there another hand? No?
You want to reinforce that at all? A secondary reinforcement?
It's a fair question. The question is, would you reinforce it all? I guess if I heard you from here, everyone probably heard. It probably takes some analysis to think through what the loads were on the building. If we think that the rebar is still elastic, did it just stretch out and crack the concrete, but the rebar hasn't yielded? Or has it done enough work that that rebar has now sort of absorbed some of its nonlinear behavior? Its post-yield. Is it that paper clip that's now not snapped back to its full original position? And if so, it might consider supplemental reinforcement. It might consider things like a carbon fiber wrap that you could wrap around the perimeter. That's probably the most practical solution for something like that. So to make that determination is probably a little bit more of an analytical question, and this is one wall of overall building, so really takes a lot more holistic evaluation of how the loads were distributed within the building to fully make that determination. But good questions nonetheless. Here's another example from the Anchorage earthquake from late 2019, where there's a bunch of questions about cracking. Apparently our team, I wasn't there personally, looked up some of the photos and even looked in the cracks, and there's a bunch of debris, and basically became evident that those cracks were there before the event. So one tool in your tool belt is really getting into the nitty-gritty of the cracks and seeing if there's moss forming and weeds growing out of it or debris. And in some instances, owners of buildings might be concerned about a crack that actually was there beforehand. So here's another high-rise building. This is also from that Chile event, reinforced concrete shear wall building, 30, 40 stories, if you do the count. How do you characterize this damage here? You have these balconies connected to these walls at the joints. There's some damage. Relatively superficial, the plaster and maybe a little bit of the concrete cover, the concrete that's outside of the confining reinforcement. So it's, outside of the pop can, we have a little bit more concrete to kind of cover things up. So that's fallen and fallen off. Certainly for a high-rise building in a dense urban environment, a concern in and of itself, because spalled concrete can be a concern. I think the thing that's interesting about this particular damage, this is total speculation, but there's not really a lot of lateral system going into those. There's just these balconies. So it made me wonder if there was vertical acceleration. A lot of what we've been talking about today has been horizontal motion from earthquake, but there are vertical components, and if there was maybe some resonance with the stiffness of those particular balconies, sort of going up and down and creating that joint cracking. In general, are we more concerned about lateral movement from earthquakes or vertical? Probably lateral, because that's the first we've talked about vertical, and we're 6 hours into the day. Why do you suppose our primary focus is lateral accelerations? Well, sorry?
Because the force, you get much higher moment down here at the bottom.
Yeah, we have our, use my model. Laterally, we have to design the building to do that more or less, actually to do that, even though that was 1 plus G. When we design buildings for gravity, we take the dead load of the building, we multiply it by a factor. We take the live load of the building, so say an office building, as many people as realistically, as much stuff could fit in that based on the design codes, and it's pretty maximized. And we multiply that by a factor 1.6, then we reduce our capacity. So we inherently build in a lot of factor of safety just by the way that the design codes work and our gravity systems. So if there's some acceleration on top of that, generally speaking, that hasn't been the major contributor to building damage, even though this balcony cantilever may be one brief example of that. A little bit of tangent, but worth a discussion. So that was the balconies. This is the lower floor of, to remind ourselves, we're talking about that building there. Scale 1 to 10. Maybe this is by definition 0 in that portion of it because you can actually see blue sky daylight. The thing to keep in mind with reinforced concrete shear walls, and this particular context in Chile, is at the end of our walls, we put reinforcement as if there is a column because of those arrows that Rami showed earlier. You know, when it's rocking back and forth, it's a lot of compression on the end of the wall and tension the opposite. I might just spit a bubble, and vice versa. Apologize for that. And so we detail a reinforced concrete column. We detail this at the end of the wall, ideally. The term we use for that is boundary zone reinforcement. In this particular building, they didn't have that. And so when you look at reinforced concrete shear walls, just something to be aware of that ideally they would have a column embedded into the end of the wall. In this particular context, they eliminated that requirement from their otherwise US-based reinforced concrete design code. And that was the consequence of that. Here's another just catastrophic example of a high-rise building. This is the roof, and that is the foundation. Here's a side view of this high-rise building that effectively toppled over, and it was also resulting from the inadequate reinforcement tying that reinforced concrete shear wall into the foundation. Obviously a catastrophic failure. The tricky part, just from a societal standpoint with this particular building, is this is 1 year old at the time of the earthquake. Oops, I guess I don't. I have another slide that shows the original construction because it was 1 year prior to the 2010 earthquake. And there was across the street a copy-paste building, also brand new, that had virtually no damage whatsoever. I think in part because it was oriented the other direction and there's some directional nature to this particular earthquake, and you can see just based on the footprint being sort of long and narrow, had very different dynamic characteristics in the sort of a weak axis compared to the strong axis of the overall global stiffness of the building. So this building has been on the news all over the place because it's such a catastrophic failure. What do you do with that other building? Who wants to live in the building that is copy-paste of the one that was all over the news for falling over in such a dramatic and tragic fashion? So, you know, as a municipality, hopefully we don't have to deal with that here, but those types of questions with, guess we're done here, with sort of communication to the public and those social concerns of we have all of this building stock that wasn't impacted and others it was, and they appear to be identical, and you know, really just navigating those things are some of the realities municipalities have to deal with. That was a shear wall building. This is shear wall with gravity frames. This is our more modern high-rise building with a concrete core wall in the middle and gravity frames on the outside. I still swear I'm feeling some light adjustment going on, but maybe I'm just having an aneurysm, I don't know. Concrete construction, here's damage to those exterior columns. Here's stereotypical X-cracking. We know that's bad, we talked about it. Remember this one? We gave it, I think, a 1 or a 2. Or this is another photo of that same non-ductile concrete frame parking garage. This was the aftershock. This is why we tag our red buildings red, is, you know, if someone could have obliviously parked their car in that garage without, you know, being deferred by a red tag, the aftershock is what brought that really brittle reinforced concrete. So here's the rest of the story for that high-rise reinforced concrete building with a setback and inner-story collapse. It was largely due to some torsional behavior of the building overall. So a lot of the work, a lot of the damage we saw concentrated on that line there was associated with what was occurring on the rest of the building, because globally there was a bunch of setbacks.
Could you say part of it?
Check this out. He asked if they were able to stay part of it. So here, that inner-story collapse. Fortunately, this particular earthquake was 3 in the morning and no one was occupying this office building. Though I remember having the nerdiest dreams afterwards. Here's some more depictions of it. Thinking about these, your typical conference room office chairs hanging off the side of the building with the glazing gone. I remember specifically having dreamed that I was in this building, but it's like the nerdiest dream because I saw the hysteresis loop. I'm like, okay, we're yielding, we're going through nonlinear behavior. Okay, we used up 50% of the reinforcement capacity. Do you guys have that dream? Is it just me? So here's some more depictions of it. That's what it looks like at the base. From a ATC20 standpoint, hopefully I don't have to say a red tag building for both the building itself as well as the adjacent corridors.
This is, we've been looking at structural things and things we don't do with rebar,
Yeah.
concrete and whatnot, but that also presumes that all materials are equal. Whereas I know in other countries, sometimes they've been known to use things like seawater in mixing cement, which is
Yeah.
the worst thing you could do. So I imagine, and like we're hearing about Turkey, it's not
Yeah.
just that the building codes were probably might be okay, but then all the backroom deals and
Yeah,
taking off.
the quality of construction, the quality of materials used for construction, the lack of inspection and quality control and oversight, at least as the initial reports have played a huge role in some of the issues, as at least for their modern buildings in comments relative to Turkey. It sounds like they're fairly modernized relative to ductile reinforced concrete detailing. So the general comment was just regarding, we're presuming quality of materials, but I think from an ATC20 standpoint, that is expressing itself, and some of these issues are a byproduct of design and construction quality, but it is good to just think through the nature of some of the damages in buildings may not be only design or configuration. It's the combination of how it's designed, how is it constructed, what materials, what seawater was used in the reinforced concrete design, mixed design versus not. All those things certainly play a big factor for sure. This is circling back 2010 and 2017. Architects spruced it up, removed a couple floors off the top, changed it to a whole new color palette, because who wants to lease this commercial office building that also was on the front page of the news because of the inner-story collapse, and it feels like a new, different building, even though it's the same structure. So whoever made the comment about did they salvage the building.
Looks like they got rid of the columns and went to shear wall.
Sorry?
Looks like they got rid of the columns and turned them into shear wall.
Yeah, actually, I hadn't really made that observation, but there's a whole new set of shear walls right there that looks like, yeah, that was originally a column. So yeah, you're right. Whole new set of shear walls that used to be gravity only. I feel better about it now. Thank you. Here's some other non-ductile performance, brittle performance of a hospital building. So one question is, a couple more depictions of this. This is really one of the case studies that led to the development of ductile detailing and also higher performance criteria for hospitals following the damage to this Olive View Hospital in California. All things being equal, you have a corner column, interior or exterior regular column, and then an interior column. All things being equal, which one are you more concerned about? The corner, the exterior, or the interior? I heard some corner. So say they're all equal, they have the same stiffness, they all took the same lateral load. Which one is taking the most gravity load?
Interior.
The interior, because the corner one is taking half of that bay times half of that bay. The exterior one is taking double that, and the interior one is taking 4 times that. So all things being equal, the interior column that you can't see is taking 4 times more gravity load based on tributary area the exterior one. All that to say, if you see the corner one, it looks bad, probably just don't go inside the building because the interior ones are probably that much more precarious just based on the additional gravity load that they're taking. Some more reinforced concrete damage, I think, non-ductile reinforced concrete damage that Rami has shown earlier. I'm just going to go quickly here. Another thing to pay attention to is there's very specific requirements in this confinement reinforcement that we talked about with this model on the size of the bar and how sharply those things, the bar can be bent and remain ductile, just like your paper clip. If you turn it a little too tight, you can snap it. Of course, it takes several cycles. And here's some examples of that where there's total fracture of these confinement bars, which may not be an intuitive failure mechanism. So something to be on the lookout for. Concrete frames and masonry infill walls. I'm going to just blast this concrete section, give us a break here, and then we can power through to the end. Concrete frame with brick infill walls. Here's some depictions of that. So we have our reinforced concrete frame. I think this kind of global two-story moment frame. Scale 1 to 10. What's the gravity? 8. What about lateral? Same. That's fair. Theoretically, these infill walls aren't supposed to be part of the lateral force resistance system. They are inherently stiff, so they took a bunch of load. There's a bunch of cracking. This is from Anchorage, I believe. Any recommendations on a posting from what you can see here? Green, or if you were to say yellow, you just keep it away from the potential falling hazard from the broken CMU infill wall construction. Tilt-up concrete shear walls, another archetype of concrete construction where it's a tilt-up wall, meaning they pour it. They either bring it from off-site or pour it right on the site, and then they tilt up the walls together. It's very common for our, sorry? Yeah, for our warehouse construction, thank you. And so the isometric view here depicts a couple things to look for. Certainly the walls leaning out of plane, the interface between the walls can be damaged, but predominantly historically the big concern has been separation failure between that connection of the exterior walls falling out of plane, pulling away from the building from the wood framing roof structure. And there's this occurrence that we discovered, particularly in buildings constructed pre-early 90s, I believe, called cross-grain bending, which means we have this wood ledger beam. Great, we've got it anchored into the exterior concrete wall. We got the wood framing roof tied into it. We got a hanger. We got our plywood sheathing, all good. But as the depiction suggests, you think of the load path, it's really kind of coming from the top, from that sheathing, nailed into the top of it, and it just grabs that ledger beam, and it's very weak across the grain, as you might intuitively expect. And so that's been the failure mechanism for a lot of tilt-up concrete buildings. So something to pay attention to if you're asked to evaluate tilt-up concrete buildings, because it can create that kind of failure, but because of a cross-grain bending failure mechanism. So here's some depictions of that. In fact, if you look up closely, you can literally see how that ledger beam is torn in half, and in some cases the sheathing was torn up as well. Other things to look for, here's some concerning cracking at this pilaster protruding from the wall supporting this this wood beam. Some more failure of tilt-up walls out of plane, unsafe condition, obviously from the exposure to wind there. That's tilt-up walls. The last is precast concrete frames with shear walls. Maybe just generally talking about which types of buildings are considered ductile and non-ductile. So is reinforced concrete construction ductile? It depends on the detailing. Hopefully we hit that home. What about wood framing? Generally speaking, if things are tied together pretty well, it's ductile. Wood framing can be non-ductile, like those videos we saw from Japan. What about steel? Does So ductile or non-ductile, generally speaking. I literally am hearing crickets. You hear that? Birds, but yeah. They're on cue. I asked them to come fly by right now. Steel, the material itself is inherently ductile, just like our paper clip. The configuration of it generally should be, particularly with modern requirements, but as we learned from that 1984 Northridge earthquake, it can fracture welds in a non-ductile manner. What about masonry? So unreinforced masonry, we've seen a bunch of examples of that, are definitely non-ductile and it's heavy, kind of the worst of the worst. What about fully grouted reinforced masonry, like CMU wall buildings, like a Costco? It can actually be relatively ductile, maybe not as ductile, but it can be pretty ductile. So all it depends. I say that to say, what about precast concrete? It all depends on the connections. Is precast concrete redundant or non-redundant? I'll keep us going here. So the thing with precast concrete to think about is it's all these parts and pieces that are cast off-site and brought together, and it's really how they're detailed. But if one element fails, there's not a lot of redundancy because it's really just it's a part with two supports. And so the key of precast concrete construction is all the connections between those precast Jenga pieces. Here's some isometric depiction of that. Stories out of plumb, beam column separation, wall separating from the wall, etc. Here's typical precast construction. And because it's so non-redundant, when it's not tied together well, it can have catastrophic failure as such. Here's a depiction of a precast corbel, this little protrusion supporting this beam, cracking and shearing off, and so they've shorted up with a wood post. Here's some interface of precast concrete panel zone. I think this is also a tilt-up as well, occurring right at this welded joint. Some more occurrences of that from Anchorage. So that's concrete.